Good morning everyone. So today we are going to start a new module which is related to the linear transformation. To reach to linear transformation, first we are going to introduce the concept of matrix transformation. So let us see this example, and what we want to see is that we want to see the reflection of xy about y-axis. In that case, if I have to define a map, I should define it as t of xy is equal to minus x comma y, or I can say that t of xy should be minus 1 0 0 1 and xy. So we are applying a map T on xy, and on the right hand side we are multiplying a matrix to xy that gives us the required transformation. This leads us to the concept of matrix transformation. So let V and W be the two vector spaces. Then we say that f, which is a function from V to W, is a transformation from V to W. In case V is equal to W, then we say f is an operator on V. So let's assume that we are thinking of a map from Rn to Rm. So in that case, x1, x2, xn belongs to Rn, and f1, f2, fm are real valued function on n variable. Now define a map from Rn to Rm such that t of x1, x2, xn is w1, w2, wn, where of course each wi is a function of x1, x2, xn. Now in particular, if we define w1 as a linear combination of x1, x2, xn, it's a very particular case because wi is a function of x1, x2, xn. It can be defined in many ways, but if it is defined like this, then we can express our given transformation as t of x1, x2, xn is equal to ax, where t is a matrix transformation. It means that if you can express any transformation t of x in the form of ax, then we say t is a matrix transformation. If you see this example where t of x1, x2, x3 is defined as follows, so I can write t of x1, x2, x3 as 1 4 minus 1 2 7 1 and 1 3 0 x1, x2, x3, and therefore t is a matrix transformation. So if t is a matrix transformation, then we must write t of x is equal to a of x, where a is said to be the standard matrix. Again the same example for which we have already computed the standard matrix, which is as follows. Now if you see the following exercises, you will observe that it is not straightforward to check that the following transformations are matrix transformations or not, and therefore we need a more refined method to check if the transformation is matrix transformation. So we are going to introduce the following theorem, which says that let T be a matrix transformation from Rn to Rn, or it is a matrix transformation if and only if the following properties holds, and the properties is T of u plus v. So u plus v, here it is a vector addition between u and v, should be equal to T of u plus T of v, and similarly T of k dot u is equal to k dot T of u. If both the condition holds, then we say that T is a matrix transformation, and if any one of them does not hold, then we say T is not a matrix transformation. And we will see that how easy it is to check the given transformation is matrix transformation or not using the following two conditions. But before that, let's quickly see the proof of this theorem. So if we have given T is a matrix transformation, we need to show that T of u plus v should be equal to T of u plus T of v, which is simple because T of u plus v is a times u plus v, which can be written as au plus av, and that gives me T of u plus T of v. Similarly, I can show the second property. Converse is little bit tricky, which says that if these two properties holds, then I must show that T is a matrix transformation, which means to prove T of x is equal to Ax. There we need to show the existence of a matrix A. Now with these two properties, I know that I can write T of k1 u1 plus k2 u2 plus kn un or kr ur is equal to k1 times T of u1 plus kr T of ur. This is easy to follow. I am using both the properties. Now let A be a matrix. I am defining a matrix, and I will show that for this matrix T of x is equal to Ax. So let A be the matrix, which is defined as A is equal to, the first column is T of E1, where E is the standard basis vector. The first entry is 1 and all other entries are 0. Then T of E2 and so on T of En. This is how I define the matrix A. Yes, if A is defined like this, then if I multiply x to A, then here also x1, x2, xn would be multiplied, and it will become x1 T of E1 plus xn T of En. Now I have given these two properties. Using these two properties, I can take x1 inside, and this becomes T of x1 E1 plus xn En. Now recall that E1, E2, En are the basis vectors of Rn, which means that any vector can be expressed as a linear combination of E1, E2, En, which is vector x. So here we have expressed x as a linear combination of E1, E2, En, and this leads us to A of x is equal to T of x, which is what need to be proved. So now if we see some exercises, so we have to see that the following are matrix transformation or not. So let u and v belongs to R2 such that u is equal to x1 y1 and v is equal to x2 y2. I have to show that the following two properties which we discussed in the last slide should hold to show it is a matrix transformation. So now T of u plus v becomes T of x1 y1 plus x2 y2, which is same as T of x1 plus x2 y1 plus y2. Now it is given that T of xy is 2x comma y, so this becomes 2x1 plus 2x2 comma y1 plus y2, which can be written as 2x1 comma y1 plus 2x2 comma y2, which is T of u plus T of v. Similarly, quickly we can show that T of k times xy is T of kx ky, which is 2kx, and ky, which is k times 2x comma y, which is k times T of x comma y. So both the property holds, and therefore it is a matrix transformation. Let's try one more question. Again I will write down T of u plus v, which is x1 y1 plus x2 y2, which becomes T of x1 plus x2 y1 plus y2, which is mod x1 plus x2 mod y1 plus y2. Yes, if I compute the right hand side, which is t of x1 y1 plus t of x2 y2, this becomes mod x1 plus mod y1 plus mod x2 plus mod y2, and which is mod x1 plus mod x2 and mod y1 plus mod y2. So this is my left hand side and this is my right hand side. The both must be equal to have T as a matrix transformation. But we can easily produce the counter example where mod x1 plus x2 is not equal to mod x1 plus mod x2, and therefore it is not a matrix transformation, but this one is a matrix transformation. So these are few exercises as an homework. If you try, they are easy to follow. And now once we introduce the concept of matrix transformation, which is defined from Rn to Rm, next will lead to the concept of linear transformation, which is defined from one vector space to the other vector space. Thank you very much.